Okay folks, so today's video we're going to look at the properties of covalent substances, and that falls into two categories. We're going to look at the properties of simple molecular substances and giant covalent substances. So the first one, what is a simple molecular substance? Well, to know what simple molecular substance is, we have to just do a very quick recap on a covalent bond. So a covalent bond is between two non-metals. So in the periodic table, it's that section there, this bit. So it's between two non-metals and they share a pair of electrons. So just look at a really simple one. So if we look at hydrogen, so hydrogen's got one electron. So if I draw my hydrogen, it's got one electron and it wants to have a full shell to be stable. So it's got one. On the first shell you only need two to be stable. So it buddies up with another hydrogen and then they share those electrons. So they've both got two electrons for this one and two electrons for that one. So they've both got a full out shell and they're stable. A different way of showing that, different way of representing that diagram is to have H with a line and then H, and that line represents that covalent bond, those sharing that pair of electrons. So you can just draw it like that. And then I've got some molemods here. So that this hydrogen, these are all hydrogen molecules. So that is two hydrogen atoms, one hydrogen atom, another hydrogen atom, and that grey bit of plastic in the middle represents like that stick, if you like. So that is a hydrogen molecule. So what's a molecule? Two or more atoms bonded together. So these are our hydrogen molecules. Go through just a few other examples. So if we were looking at water, so water is H2O. So if I had my oxygen, it's got 1, 2, 3, 4, 5, 6 of its own electrons on the outer shell, and it buddies up with a hydrogen there and a hydrogen there, and so you could draw that as H stuck to O stuck to H. So those two are that stick and those two electrons are that stick, and then so you can represent that like these. So this is the O, so H2O, two H's and an O with the two bonds there. So that's what, these are simple molecular substances. They're called simple molecular substances because they're quite small, simple molecules. There's only 3 atoms in this one. So we had CH4, and CH4 is methane. So we've got methane here. We've got the black one is the carbon. So we've got 1 C and 1, 2, 3, 4 H's. So CH4, that's a simple molecule. So simple molecular substances, quite small, straightforward molecules. You need to know what the properties of those are. And by properties, it means what are their boiling points, what are their melting points, do they conduct electricity? Those are the ones that we're mainly concerned about. So that brings us on to one of the first new keywords for today, which is the word intramolecular. So an intramolecular force. And this first part is the key, intra. Intra means inside. If you think of somebody in hospital, if they were on a drip, that means they're getting drugs or food administered to them. Intravenously. So intravenously, they're getting medicine put inside their veins. Venously, because it's like veins, and intra meaning inside. So intra means inside or within. So something that's intramolecular is something that's inside a molecule. So intramolecular and intramolecular force. So we've got our water molecule there. It's like the bonds. the bond between the hydrogen and the oxygen, the grey bit of plastic there, it's an intramolecular force, or a bond. They are bonded together, and that is quite a strong bond. It's difficult to pull these apart because they're sharing electrons. Like with this diagram, intramolecular forces, intramolecular bonds, that they're sharing those electrons. That's difficult. It takes a lot of energy to pull those apart. But that leads us on to the next word, which isn't intramolecular, it is intermolecular. And an intermolecular force, intra means inside, inter means between. So if you think of an international flight, can't spell, international, between nations. So you're flying internationally, you're flying from England to America. Or an international football game is between France and Spain. So they're between nations. Or the inter-house cup in schools, when one house plays another house. So inter means between two, and intra means inside. So if we were talking about an intermolecular force, that is the force between two different molecules. So if I stick in, let's cover my floor in water. Warning, wet floor, don't slip. Right, let's cover my floor in water. Let's actually do that on a whiteboard. So the grey bits, the bonds, the intramolecular bonds, it's very difficult to pull these apart because it's those shared electrons holding them together. But there isn't very much force between those dotted lines. It's a really weak force between these two molecules. Intermolecular force, like the internet, different computers linked together. Intermolecular forces, the force between different molecules. There's almost nothing keeping this one in place. These three dotted lines are really, really weak forces. So it means it can just move over there for a little bit. And then that one can move over there, and they can all move around. They've got really weak intermolecular forces. So simple covalent compounds, going back to the start, simple molecular substances, they have very low boiling and melting points. Because, so if you remember, if something's a solid, it means they're all really closely packed together. So I've got some nice ice there to cool my drink down. They're all nice closely packed together, but it doesn't take very much energy at all to melt this and move them far apart. And it takes, again, not very much energy to boil it, turn it into a gas, turn it into some steam, and move them further apart. Why doesn't it take much energy to do that? Because the intermolecular forces, between molecules, are very, very weak. So that is why simple covalent substances have very low boiling and melting points. And that leads us on to the next property of them, which is about conducting electricity. If you think about what electricity actually is, so just draw battery. So you've got a battery. Let's connect it up to Edison light bulb. We need two wires, so a wire going in, wire going out. So then our light bulb lights up. So what is electricity? Well, it's electrons moving down a wire. So we've got our little electrons. If you remember, electrons got a negative charge. So we've got all these electrons moving through the wire. I'm just going to get a different colour pen. So the electrons moving through the wire, and they go along up through there and out that way, out through the battery. So that's what you tend to think of electricity as, is electrons flowing around. But if you actually just go one step further, electrons have a negative charge and they're moving. So electricity is actually flow of charge. And flow is just a fancy word for movement. So when you think of electricity, you need to have, for there to be electricity, you need flow of charge. So charge is positive or negative, and flow is a fancy word for movement. So for something to conduct electricity, you need charges that can move. And if we go back to our covalent compounds, you pick any, or let's pick methane, so CH4. Actually, let's make it a bit simpler. Let's go with smaller molecules. It's the same for any of them, but let's go with some chlorine, some Cl2. So, can these molecules move around? And they are doing so because it's impossible to keep them in one place on camera. But can they move around? Yes. Why can they move around? Same reason we've just talked about. They have very weak intermolecular forces. There's very little keeping this one close to that one, so they just go all over the place. So they are free to move, but they don't conduct electricity because there's no charges here. So if we look at the one molecule on its own, it's made of protons, which are positive, and electrons, which are negative, but because it has exactly the same number of positives and negatives, that means overall the charge is 0. So if it had 10 protons, it's going to have 10 electrons, plus 10 minus 10 equals 0. So yes, this molecule can move over here, but if it moves over there, it means there's no charge because we've got positives and negatives moving. And if that one moves over there and that moves over there, and they can all be moving as much as they want, but they don't conduct electricity because there's no overall charge that's moving. To have electricity, you need to have like all the positives going one way and all the negatives going the other way. Well, if this one goes over here, there's positives and negatives in it, so they cancel each other out. So you don't have a flow of charge. So even though the simple covalent substances, simple molecular substances, can move around, because they don't have any charge in them, they don't conduct electricity. So now we're going to talk about, go back to my first one, we're going to talk about giant covalent substances. So clues in the name for giant, they're massive. So if I get some diamond here, so diamond made of carbon, and if you look, this is a really small sample of it really. Ideally this molecule would be like, this model would be like 500 times bigger, but if you look, if I pick this particular carbon here, you can see it's got 1, 2, 3, 4 bonds. The ones on the outside, like this one's only got 2, but that's because really the model should carry on, so there should be loads and loads and loads of them, all with 4 bonds. So when you're looking at a diamond on some jewellery or diamond necklace or anything like that, what you're actually seeing is one huge molecule, and the molecule is so big that you can see it with your naked eye because it's just huge. So what this means is it's got an incredibly high boiling and melting point. When we look at our simple molecules, whilst the intramolecular force, remember intra, inside, that is really strong because it's the bond, so it's difficult to pull that apart, but the force between two of them, intermolecular force, is really weak, so it's easy to pull apart. If we look at diamond, if we say diamond is one huge massive molecule, there are no intermolecular forces because it's one molecule, so you don't need forces between molecules. If you want to melt diamond, you've actually got to break the intramolecular force. You've got to break all of the bonds. You've got to break the covalent bonds, which takes a lot of energy to do, which is why diamond has got an incredibly high melting point. So simple molecular ones, low boiling and melting point because the molecules are easy to pull apart because of weak intermolecular forces. Giant ones, very high boiling and melting points because to make them melt or boil, you need to overcome the intramolecular force. You need to overcome and break all these bonds. And breaking those bonds takes a lot of energy, which means a high temperature, which is why diamond melts at incredibly high temperature. So that's the boiling point of these. And I've got an example here. I've got graphite, which is a different form of carbon. So if you look, instead of 4 bonds in graphite, everything's got 3 bonds, but it's kind of in layers. So it's like this honeycomb, and it's in layers. It has very high boiling and melting points because of the intermolecular forces. Intramolecular forces are very hard to break because you have to try and break the bonds. Same as diamond. And going on to, do these conduct electricity? Well, diamond definitely doesn't conduct electricity because there are no... Remember, for electricity to flow, you need charges that can move. Diamond doesn't have... None of the particles in diamond can move anyway because they're all stuck together. So it wouldn't matter if it had charges, but it doesn't. So diamond does not conduct electricity. And that's the case for virtually all giant covalent substances. They do not conduct electricity. Graphite is the exception, and this isn't a perfect model of it, but if I put it sideways, these purple bonds are the electrons in between layers, and they're free to move around, which is why for graphite, the layers can slide over each other. So really the best model of graphite would be if I pull this layer apart, and then it's like the layer is a really strong bond, but the bonds between the layers are weak, and so the layers can slide over each other, which is why when you use a pencil, which is made of graphite, and you put your pencil on the paper and make a mark, you actually snap a layer off and leave the layer behind, which is what you can see on your pencil page. But graphite does conduct electricity, and the reason it's able to conduct electricity is these electrons in between the layers can move. So electrons are negative, they have a charge, they can move. So you've got charges that can move, which means you've got a flow of charge, they can conduct electricity. So graphite is one of the only giant covalent substances that can conduct electricity, and it's because the electrons in between the layers can move. So, really quick summary, if we had, so our simple and giant ones, so we've got melting points, boiling points, and conducting electricity. They've got really low melting points, really low boiling points, because they've got incredibly weak intermolecular forces. Giant ones, very high boiling and melting points, because the intramolecular forces inside those giant molecules, you have to pull the whole molecule apart to melt those, so you need very, very high temperatures to do it. Do these conduct electricity? No, because whilst they can move around, there's no charges there. Do these conduct electricity? No, because they can't move around. And the only exception, so little asterisks, is except graphite. Hopefully that makes sense.